Good morning and welcome to our performance analysis on the Bombardier CRJ200. In our investigation, we'll be analyzing different takeoffs on the CRJ200 and how it performs. We'll be analyzing principles from aerodynamic study guides from week 3 to 7 to help guide us. Some of these principles we'll be looking at for task 1 and task 2 are the takeoff and thrust generation equations at both high and low altitudes, lift drag characteristics such as thrust available versus thrust required, lift equations, as well as examining extreme load factors, and implementing design change factors. Using X-Plane as our flight simulator, as well as helping us acquire data, we can hopefully showcase these principles through X-Plane and can be applied to real-world scenarios. For our task, we'll divide into two main sections. First, we'll be determining the minimum thrust required for safe takeoff at Brisbane Airport at standard sea level conditions that the CRJ can operate at. And by doing this, we will help provide evidence for our principles, how different factors can impact takeoff, and how this can integrate to real-world applications, showing us what happens if thrust is too low. Then for our second task, we'll be applying the reduced thrust setting that has been found from the first task and to use this at Cusco Airport. This high altitude location will help determine whether the aircraft can still take off, as well as if a design modification is needed to improve performance. The end of this task should show how density altitude impacts aircraft performance and how the overall performance can be improved throughout other aerodynamic principles changes without the additional thrust needed. Lastly, this then reinforces the necessity of long runways in high altitudes for airports in the real world.
To help set us up for task 1, we'll be using the CRJ200 aircraft at Brisbane Airport runway 01 left, with the aircraft set to maximum takeoff weight, which is about 24,040 kilograms. At this weight, it gives us a worst case scenario as well as help outline the direct effect on the thrust to weight ratio. This also provides us a consistency across the trials. Since we are at Brisbane Airport, that is close to sea level, the air density won't have much effect, meaning that the engines can produce the rated thrust and achieving close to max available thrust. To find the estimated minimum thrust available, we began to gradually reduce engine thrust in intervals of 20%, starting from 100%, 80%, and 60%. However, at 40%, it didn't take off. This meant that we had overshot the estimated minimum thrust available. So we went back to 50%, 45%, and at 43% available, the aircraft used up all the runway to take off, resulting in our estimated absolute minimum thrust available during the simulation. Through this test, we can find estimated minimum and then find and compare theoretical minimum thrust. On this slide, we're looking at the takeoff distance equation from week 7. This equation takeoff distance depends on liftoff speed, gravity, and the thrust to weight ratio. By rearranging this equation, we can solve directly for the minimum thrust required using the CRJ200 at maximum takeoff weight with a liftoff speed of 1.2 times stall speed and Brisbane's available runway length. We calculated the minimum thrust to be around 4,143 pounds of thrust. When we compare this to our simulation in X-Plane, which gave us about 3,965 pounds of thrust, the difference is small, meaning that X-Plane has real-world applications. Here we've moved from the runway physics to the jet engine fundamentals covered in week 4. The equation shown does have more involved, as per week 4 of the aerodynamics 2 syllabus. However, for simplification purpose, this is all that we needed. This tells us that thrust is produced by the change in momentum of the airflow through the engine. To apply this, we first calculate the mass flow rate of air entering the engine. That depends on air density, inlet air, and the velocity of the air going in. At liftoff speed, which is about 80.3 meters per second, we calculate the mass flow to be roughly 96 kilograms per second. This sets the foundation for determining the thrust the engines can actually provide at rotational speed which links engine design directly to performance. Next, we need to calculate how much thrust is actually available at lift-off speed using the jet thrust equation. We took the published maximum thrust rating for the CRJ200's engine, which is 9,220 pounds at sea level. However, this value is the ideal rating and doesn't reflect real conditions during takeoff. To account for thrust loss due to drag, inefficiencies, and thrust lapse at rotation, we scaled this by 0.8. That gives us an adjusted thrust of 7,376 pounds, or about 32,810 Newton tons. Next, we found our exit velocity. By using these following values, 32,810 newtons as our thrust value, 96.3 kilograms per second for mass flow rate, and an inlet velocity of 80.3 meters per second when substituted into the equation shown in the slides gives us our exit velocity of 421 meters per second. Finally, we calculate the thrust directly from the momentum equation, which gives us 32,844 newtons, or converted to 7,844 pounds. This value is the thrust available at liftoff speed, which is lower than the rated maximum, but much more realistic. It reflects the fact that static thrust values can't be applied directly once the aircraft is moving, and aerodynamic drags comes into play. This slide puts the two results side by side, showing that at Brisbane, at understanding sea level conditions, the CRJ200 has comfortable thrust margin. This margin is essential for safety. It ensures the aircraft can accelerate fast enough not only to reach takeoff speed, but also to allow for a rejected takeoff if necessary. This video visually shows what effect a higher available thrust level has on the aircraft, as it was able to accelerate faster and achieving rotational speed at a distance of 4,324 feet, while at a lower available thrust, the aircraft can be seen experiencing a slower acceleration during takeoff roll, as well as significantly increased ground distance required to take off. This is further backed up by this graph, as it shows a relationship between thrust and takeoff distance from our X-plane simulation. As we gradually reduced thrust from 100% down to 43%, you can clearly see that takeoff distance increased dramatically. For example, at full thrust, the aircraft lifted off at around 4,324 feet, but at 43% thrust, it required over 11,000 feet of runway. This highlights the inverse relationship. As thrust decreased, distance increased. Importantly, at 43% thrust, the CRJ200 was only just able to take off at a runway at the very end of Brisbane's runway. This matches with our earlier calculation of the minimum thrust requirement of about 4,143 pounds. This graph also ties directly to real-world implications. Airlines cannot risk operating their minimum thrust because it removes the safety margin for rejected takeoffs or unexpected drag factors. That's why manufacturers and operators always plan performance with excess thrust available. For the last part in task 1, we calculated the time required to accelerate to liftoff speed using the week 7 time equation. With the thrust required scenario, the time comes out to about 86 seconds, which is clearly impractical. But with the thrust available from the engines, the time drops to 48 seconds, which is realistic and safe. This demonstrates the importance of having thrust available, well above the theoretical minimum. Only having the thrust required value results in the aircraft having a chance to still get airborne, also leaving the acceleration to be too slow and have no safety margin. For our task 2, we tested the CRJ200 at Cusco Airport in Peru. This location sits at a very high elevation. At this altitude, the air is thinner, meaning that the wings generate less lift for the same speed, so the stall speed goes up. Second, the engine intakes less air, which reduces the thrust they can produce. In our experiment, we set the maximum thrust equal to the minimum thrust of about 4,143 pounds. This gave us a thrust-to-weight ratio of just under 0.08 smaller than at sea level. As expected, with this limited thrust, the aircraft could not take off in clean configuration at Cusco. To solve this, we applied a design modification. We increased the maximum lift coefficient by deploying flaps, which allowed the aircraft to generate more lift at a lower speed. With this change, the aircraft was able to be airborne within the runway length in X-plane. This emphasizes why airlines rely on efficient lift generation and long runways at airports like Cusco. For the next section in task 2, we look at stall speed equation, which the stall speed equals the square root of 2 times the weight divided by air density, wing area, and the maximum lift coefficient at Cusco. The air density is much lower than at sea level. If we leave the aircraft in clean configuration with a maximum lift coefficient of around 1.5, the stall speed is about 164 knots, and the liftoff speed, which is 1.2 times stall, jumps to almost 200 knots. That is extremely high for a regional jet. By adding flaps, however, we increase the maximum lift coefficient. With flaps deployed, the stall speed dropped into the 130 to 140 knot range, while the liftoff speed came down to around 160 to 170. This demonstrates the trade-off. Flaps reduce the liftoff speed, which helps with runway performance. They also add drag, which slows acceleration. So there is an optimum setting. In our simulation, around 20 degrees of flap gave us the best balance. Finally, we looked at how all of this affects the takeoff distance. Using the same equation from task 1, this video shows what happened, which was that we capped the thrust available to 4,143 pounds of thrust and set wings to clean. The model then gave us a takeoff distance of more than 4.5 kilometers, which is far longer than Cusco's runway, which is around 3.5 kilometers. Even with flaps rising, the lift coefficient, the simple equation still predicted that the aircraft would need more runway that was available. However, when we ran the test in X-plane with 20 degrees of flap as shown in this video, the CRJ200 was able to get airborne safely. So why the difference? The simplified equation assumes constant thrust. It ignores ground effect and does not fully model how flaps change both lift and drag. X-plane includes all of those details, which explain why it performs better. At high altitude airports with low air density, the stall speed increases, resulting in thrust-to-weight ratio to decrease, meaning our takeoff distance increased. In conclusion to task 2, Real-world solutions have been implemented which include high lift devices, weight restrictions, favorable winds, and longer runways. This task shows both the limits of simplified theory and the value of simulation in demonstrating how design changes can ensure a safe takeoff and be applied in the aviation industry. While Task 1 is highlighting how thrust directly governs takeoff performance, comparing theoretical calculations of about 4,143 pounds, while the simulator results was 3,965 pounds. This close match validates the equation, as well as this task shows the critical importance of maintaining adequate thrust margins for safe operations and rejected takeoffs. This is the end of our presentation. Thank you for listening. The credits go to my partner Alex Barbulo and me, Macavilli Smythe. The workload is split evenly.